For our next topic in KSP, we're going to take a look at what's known as the common ion effect. The common ion effect is an application of Le Chatelier's principle, but we can also quantify it. On the AP exam, they'll most likely ask you to describe the solubility of something when a common ion is present, but they may ask you to quantify it. So for example, we have this reaction, which is the dissolving of calcium phosphate into calcium ions and phosphate ions. If we have a solution that's already at saturation, it means these two things, the calcium and the phosphate, have already been maxed out, and as much of this that's dissolved that could dissolve already did. By Le Chatelier's principle, what would happen if I added more calcium at this point? At this point, if I added more calcium and I increased the concentration of that, we would get a left shift. If we got a left shift, then less of this would be dissolved, or we could say that we have a decrease in solubility. And in fact, we will always have a decrease in solubility when a common ion is present. If I were to think of it this way, where the Ksp value equals the concentration of the calcium ion cubed times the concentration of the phosphate ion squared, and again, we have no denominator because it's Ksp, I would realize that the product of these two, the calcium and the phosphate, has to always equal the same value. So that would mean that if one of those values went up, the other one's value would have to go down. So once again, anytime we have a common ion, we have a decrease in solubility with a common ion present. Now we're going to take a look at how we might quantify a problem like this. I have written a problem here, it's also listed in your notes, where we're going to compare the molar solubility of lead chloride in pure water, lead nitrate, and sodium chloride. When we say the molar solubility, remember that the molar solubility is given by S. So first I'm going to solve it in pure water. I need to write a dissociation reaction. PbCl2 dissociates into Pb plus 2 and 2Cl minus. Writing my Ksp expression, it's going to be lead times chloride squared. And I'm, again, no denominator. I'm a little lazy with the phases, but it's always going from solid to ions. Filling in my chart, I'll have 0 plus S, 0 plus 2S, and at equilibrium we have S and 2S. Plugging into my Ksp expression now, we'll have the Ksp, which is 1.6 times 10 to the negative fifth, equals S times 2S quantity squared, or Ksp equals 4S cubed. So I'm going to take 1.6 times 10 to the negative fifth, divide by 4, and now I'm going to, oops, I entered that wrong, 1.6 times 10 to the negative fifth. I'm going to divide by 4, and now I'm going to cube root my answer or raise it to the 1/3 power. And I get the molar solubility to be 1.6 times 10 to the negative 2, or 0.016 moles per liter. That tells me 0.016 moles of lead chloride can dissolve in every liter of pure water that's present. Let's take a look at B now. The major difference between A and B and C is that in B and C, we have initial concentrations of one of these ions, meaning one of these two does not start at 0. Taking a look at B, B tells me instead that we're starting with 0.1 molar lead nitrate. Lead nitrate's fully soluble. That means the concentration of the Pb is going to be 0.1 molar to start. So rather than having a 0 here, I'm going to have a 0.1. I'll have a 0 there, plus S, plus 2S. Now, here's where you need to consider, is S going to be a big number or a small number? It's almost always a really small number. And since it's a really small number, I can make an assumption here. And I'm going to assume that 0.1 plus S is basically still 0.1. That allows me to put a 0.1 here rather than 0.1 plus S. The advantage of that is I don't have to try to solve a third degree polynomial now, which is great. And it's mathematically going to be about the same. These values are going to get plugged into my Ksp expression now. My Ksp value was 1.6 times 10 to the negative fifth. And that's going to equal 0.1 times 2s quantity squared, or 1.6 times 10 to the negative fifth equals 0.1 times 4s squared. Solving for s, 1.6 times 10 to the negative fifth, I'm going to divide by 0.4, and I'm going to square root my answer, and I get s to be 0.0063 moles per liter. And as predicted, when I have a common ion, in this case, the common ion is lead plus 2, it's going to be less soluble, and I have that given by this smaller solubility than I found in A. If you want to try C on your own and then come back and check for the solution, not a bad idea. If you want to just continue watching, I'll go through C. The difference in C is rather than having an initial concentration of lead, we're going to have an initial concentration of chlorine. So PbCl2, once again, the initial concentration of chlorine, I believe, was 0.15. 0.15 molar NaCl, fully soluble. So the chlorine concentration will be 0.15 molar. This starts at 0, plus S, plus 2S. I get to make the same assumption here. I'm going to assume that S is really small compared to 0.15. As a result, 0.15 plus 2S basically still equals 0.15, allowing me to put 0.15 there. Plugging these values into my equilibrium expression, Ksp is going to equal S times 0.15 squared. My Ksp value was 1.6 times 10 to the negative fifth. So 1.6 times 10 to the negative fifth divided by 0.15 squared yields an S value of 7.1 times 10 to the negative fourth moles per liter. I could have predicted that it'd be much more soluble in pure water by Le Chatelier's principle. I can prove it quantitatively.